Well, in the last lesson, we looked at the Huygens principle and how waves of light, rays of light particularly, cancel in certain places on a screen. So let's look at that again, and there's a little bit more that happens here. As we keep going up the screen, there's additional regions where the interference pattern is special and unique. So here we have the slit width A. It was slit width. And position Y from the center of the screen. Now you can think of this as looking, from the top down, the top view. And so you're looking at a screen, say left and right. That's perfectly valid. Doesn't really matter. Or you can think of it as vertical. But in any case, if there are wavelets whose energy is projected, well, for a given wavelet, all the wavelets along here, we have energy going in every direction from every wavelet. So these rays are kind of representing the wave energy from the wavelets. And in this case, we're considering the part that's just horizontal, where the angle is 0. What happens? Well, at the center of the screen, they're in the direction of the center. They arrive in phase. And remember now, this is a really small slit compared to this distance and compared to the screen. And so think of all these arriving at the center, or close to the center, and every crest is meeting the crest, and so they produce a constructive interference pattern, a bright pattern. So this is actually kind of visually what you see, all right, as you will eventually experience. So you get a bright spot of light. That's not just a spot, but it's a gradient of light, really. Brightest right in the center. All right. So now here are in both positive and negative angles. We'll just kind of consider one, but it's symmetrical around this. So theta 1. Let's look at theta 1. At that particular angle, very exaggerated here because the angle is really small in reality. But so we can see it, here's theta 1. And the rays of energy that are going in that direction that strike the screen here. Now keep in mind that theta, here's where there might be some confusion. Theta 1. For all practical purposes, they're all at that angle, essentially. All right, so I'm calling theta 1 this, but you might as well call theta 1 this one also, to the top one, because this is way exaggerated in terms of size. It's just a tiny, tiny little slit. All right, so bear with me then. Hopefully that wasn't confusing. So the direction that all these are going is here, basically to that point. Now if I draw perpendicular across there, this is a wavelength across the whole thing. Now this is what we did in the previous lesson. We looked at the halfway point. And at halfway through, if this was lambda over 2, that is where we had cancellation. So this is really showing the same thing. But for every ray in the top half, like for this one here, there is a ray in the bottom half that is a path length, a half a wavelength longer. So this one is a half wavelength longer than this one. This ray here is a half wavelength longer than this one. This ray is a half wavelength longer than this one. That makes sense. This is lambda over 2. This is lambda. The difference is lambda over 2. So in that direction, at this particular angle where this condition is met, we will have cancellation on the screen. And that's what you see right here. It cancels at this location. Now we're going to pick another angle. Let's pick theta 2. And this is a steeper angle that the rays are projected toward. Keep in mind the rays are projected at every angle, because what's coming out of here is energy, rays going in every direction from all those huge number of tiny wavelets. So in this case, we're just considering the special angle theta 2. At theta 2, something special happens when the following condition occurs. When this longest ray at the bottom is 2 lambda different than the very top. And in the middle, it's 1 lambda longer. So we got a 1 wavelength, 2 wavelengths difference in path length across there. Now in every quarter of A over of A, you know, in the top quarter, there's a half wavelength difference between this and this. So each quarter has a half a wavelength. And that means that for every ray, there's a corresponding ray that cancels again. So in this direction, the rays cancel as well. So you have cancellation at these special locations. And there we go, etc., etc. So we have this pattern showing up again, where you have the minimum energy here, 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 here. Halfway in between is going to be maximum energy. So we can do this again and see how the pattern expands. At theta 3, we get another fringe where there's bright, dark, bright, dark, bright, dark, etc., etc. Well, there is a pattern to all this nonsense we're talking about. Not so much nonsense, actually. So we end up with some right triangles that we can kind of generalize here using the specific examples of theta 1 and theta 2 that we just looked at. All right, so we have this slit with A. That is actually the hypotenuse of a right triangle. All right, so there's theta 1 and lambda, and so we can say sine of theta 1. See, sine is opposite over hypotenuse. So that's lambda over A. That is a relationship where you get cancellation of the light energy at the screen some distance away. Then we also had theta 2. Same slit width, different angle. And we had that cancellation occur at this special angle as well, where it's across the slit width. The difference in path length of the rays is 2 lambda. Then sine of theta 2 is 2 lambda over A. And it repeats this pattern. These particular angles, the path length from the rays that occur from those various wavelets along the wavefront, which exists along here, the pairs of rays will cancel. Pairs of rays within that region. And when they all do that at that special angle, then at the screen far away, you have regions where there's no light because it's destructive interference. All right, and then in between that and the next one, we get the bright line and a gradient of light intensity as it gradually goes from destructive to constructive interference, etc. So the pattern that emerges, we have cancellation of light due to diffraction, which is what this Huygens principle is all about. When, if you look at this, you can multiply by A. A sine of theta 1 is lambda. A sine of theta 2 is 2 lambda. A sine of theta 3 is 3 lambda. A sine of theta equals plus or minus m lambda. The angle could be plus or minus. And m in this case can be 1, it can be 2, it can be 3, any particular number like that. All right, actually there is a limit. You can't go to infinity or anything because this angle suddenly becomes too big and it doesn't happen anymore. But let's not worry about that for now. So the other thing to keep in mind in this whole discussion, this light that we're talking about, like if we produce water waves, we have a particular frequency. It's basically a single frequency, and so light has to have a single frequency for this to make any sense. That's called monochromatic. Chromo, color, single color. It's a single color or a single wavelength. If that wasn't true, then we have a whole cacophony of different wavelengths interfering kind of at random. They're all at different phases, crests and troughs, meeting all over the place, and you just don't get this result. It's way too complicated. The various wavefronts randomly cancel at all different places. You don't get any patterns of light and dark in that case. So we've just gone over is introduction to the idea of diffraction and Huygens principle. The result of diffraction, that you get an interference pattern based on the wave nature of light, waves going through a slit producing an interference pattern on a screen. It's called a diffraction pattern. It's a very fundamental property of nature. It's a very fundamental principle that limits, for instance, the resolution of a telescope. More on that later. So we're going to wrap that up for now and take a brief detour into refraction again and some other ideas of light. And we're going to come back to diffraction and diffraction gratings in a future lesson. See you next time.